It's great to be here. I thought I'd spend some time today to tell you a little bit about some of the work that we're doing here at UCL, at the AI Centre. And I'm not sure how well people know about UCL at University College London. So I'm also going to spend a little bit of time telling you about UCL and the history and our interest in AI. So this is going to, in general, be a very overview kind of presentation. I don't think there's a single equation in the whole talk, so please forgive me if you're looking for a more technical talk, but this is really, I think, maybe just an overview of our interests, and I think maybe
that would be wonderful, David. In fact, the whole audience is a diverse audience, so I just wanted to update you about that. And let me also, see, everybody in the world knows you well, and everybody in computer science knows you so well. David Barber needs no introduction, but as part of my duty, let me introduce for others, people who may be from other disciplines. Good evening, everyone, for people from India, and good morning to Europe and to David. And so I would just quickly introduce David. David Barber is a professor in computer science at University College London. David received a BA in mathematics from Cambridge University and subsequently a PhD in theoretical physics, statistical mechanics from Edinburgh. He is director of the UCL Centre for Artificial Intelligence, which aims to develop next generation AI techniques. And he has very broad research interest related to the applications of probabilistic modeling and reasoning. David is also a fellow of the Alan Turing Institute and a CSO of Reinfer, an AI spin out of the UCL. So without taking much time, I just pass it on to David. David, thank you very much. And the audience is yours. We have about 1 hour time, and we would be live streaming the talk on YouTube. And I hope I have the permission to record the talk so that we can upload it later on YouTube.
Sure. Thanks, Vivek. Lovely to be here.
Thank you very much. The floor is yours, David.
Great. Cheers. So yeah, so as I said, this is basically going to be a very much an overview talk of some of the things that I think are interesting about AI, but also about UCL, which may not be so familiar to some of you. So what is UCL, University College London? So it's a very big university in the UK. In fact, I think it's the largest university in the UK now, and we have something over 40,000 students per year, and we have a campus in central London. This is our main Bloomsbury campus. So it's been around quite a while, and but it's also, I think, a very progressive university. It's one of the universities which was socially the most, I think, progressive in the country in terms of admitting women students on an equal basis as men, and many other progressive social agendas. So why did that happen? Well, it actually, one of the founding sort of members of the university, or something in the philosophy for founding the university, was this character here on the left called Jeremy Bentham. And he was a utilitarian philosopher, and one of his phrases was, "It's the greatest happiness is the greatest number that is the measure of right and wrong." So in a sense, he, with this kind of idea, he really drove the sort of founding ethos of the university, that it's really about how to benefit people. And, we should really think very carefully about what we do in order to make sure we're aligned with that vision. And so UCL is very proud of that. In fact, they're so proud of this whole idea, and him in particular, that he's still here. This is him. This is Jeremy Bentham. Sat, or his skeleton, or the remains of him, are sitting here at UCL, proudly on public display. This actually is not his real head. His real head was stolen by some chaps from a rival college some years ago in London, and but it was eventually returned, and this is actually his real head here. So this whole idea of social progress and using our research for social benefit, it's really started a long time ago, and it's still there, even physically in some sense, with Jeremy Bentham. So over the years, we've been doing a lot of research in AI. So the AI Centre itself is a little bit more than 2 years old, but it's certainly much more than 2 years since we've been doing research in AI. And for example, there are many characters who've been through the university and since we've been doing AI research. But here's a sort of a handful, a selection of some of the better known characters. So Jeff Hinton was here at UCL. He's one of the leading figures in deep learning. Peter Dayan, one of the founding leading figures in reinforcement learning and theoretical brain research. Joshua Taylor, a leading mathematician in the analysis of machine learning, and Temis Asabis, among with other students, founded a company, DeepMind, from UCL, and he's still very deeply connected with UCL. So this sort of shows the depth, I think, that we've had in research at UCL, which I think has really helped to found UCL as a kind of a leading place to do AI research over the years. All right, so the centre itself sits here in a nice building in central London. We have over 100 researchers. We have lots of interest across the spectrum, really, in terms of AI research, from language, vision control, and other areas as well. We graduate also a lot of master's students every year. We think this is one of the largest graduators of master's students, certainly in the UK, if not in Europe and elsewhere. And this is really beneficial to our research, but it also helps us to maintain very strong industry partner links, because these students often do projects with leading organizations and startups around the world. So we have many companies that we partner with, and we're also very interested and keen in making spin-out creation. So DeepMind was sort of a UCL spin-out, but we're also very interested in the ongoing creation of economic value and societal value from our research. And UCL also helped found, it's one of the founding partners of the Alan Turing Institute, and we continue to have strong links with them here in central London. So, okay, what is our approach to AI? I should say maybe my approach to AI, but I think this is hopefully consistent with many other people in the centre. So what is the goal of AI? Well, it's by and large to replicate human abilities in a set of areas, including communication, reasoning, interaction with the world, emotion, and empathy. And you might ask, well, why do you want to do this? Well, in some sense, going back to that utilitarian philosophical principle, we really feel that if you can solve some of these challenges in AI, you can actually free people from very menial labor tasks. So, for example, people who are driving cars or stacking, boxes in warehouses, things which are not really using a human being to the fullest extent. They're in some sense just using a human being as kind of in some sense a manual, worker. And I think that's not really, people living their lives to the fullest in that sense. So you can free people from those kinds of, more menial labor tasks. And also you can try to make a safer, cleaner, healthier, and happier world for everybody through a whole variety of AI applications. So that's really why we want to do this. We really feel that there is a benefit to having these technologies. So that's what sits at the heart of our interest. Now, I think it's very interesting to think a little bit about the history of AI and the different approaches that you could take to trying to find some solutions to those kinds of challenges. So a very powerful philosophical principle around science is the idea of reductionism. So this means that you are trying to understand a complex process by breaking it down into its simplest parts, reducing it to interactions between relatively elementary units, which somehow ultimately explain the behavior that you observe. And this has been a remarkably successful and continues to be a remarkably successful principle behind science, particularly areas where there are underlying laws, like in physics, which seem to This suits that model very, very well. On the other hand, if you were to try to say make a duck, right? Maybe you want to build some kind of robotic duck, which walks like a duck and maybe behaves like a duck, then you might think a natural way to do that would also to be trying to reduce it to its constituent parts, like what are the internal mechanisms behind the duck? Could you build that in some kind of muscular sense? Maybe there's a brain that you could build by sort of reducing it to these elementary parts and fully understanding how a duck works, right? And building up from the ground up through that reduction. Now that I think you can imagine is going to be a pretty complicated thing to do, even if you want to just to build the reasoning capability of the duck. Understanding what's going on in the brain of the duck is a very complicated problem, and it's not so clear that this reductionist principle is going to be particularly helpful here. Well, people did try to use things like this in the past in AI. So you could talk about rule-based systems, which are maybe a little bit like this. So you might say, okay, if you are, you're trying to make an algorithm which does a diagnosis of why the TV is not working, then you might ask an expert who's a TV repairer and try to replicate the understanding that the expert has in some kind of diagram like this, where, well, does the television turn on? No. Is the power cable plugged in, etc. And you go down this tree of diagnosis, and you would then ultimately end up with some particular thing that you would try to fix. And this is kind of, in some sense, fine. It explicitly lays out all of the rules that the expert knows. It reduces all of the the information to these sort of atomic points. And it's great, you can fully explain it, and you can fully understand how the decisions are taken. But the downside is it's very inflexible. We don't know, how to answer questions which are not nodes in this graph. If you ask a question which is not present in this tree, well, what do? You don't know how to proceed. So this is a very complicated situation to be in. And in general, the kinds of challenges that we face in AI don't fit neatly within this pattern. How would you use something like this to solve the problem of, say, computer vision? How do you, recognize dogs or cats in images? This is, not really going to be, reducible in any easy sense to a picture like this. So in some sense, we're left with this challenge of like how to make something that can behave in some sense or have the results which are similar to what a human brain or an animal brain might be able to achieve in, say, visual processing. But we don't necessarily want to be able to, we don't feel that we're able to go in and totally, in a reductive sense, understand the individual behavior or the elements which are making up the brain. This seems to be a kind of a hopeless task. So there's an alternative viewpoint, which is that it's hard to explain how this thing works, this resulting object, the brain. But maybe an alternative thing, which is easier to explain, is the process by which you can result in constructing such a brain. All right. So if you think about something like maybe evolution, you would say, okay, there's some kind of genes. These genes go into some modification. There's some reproduction. Those favorable modifications and ultimate reproductions, which actually are advantageous to survive in the environment, they're more likely to survive, and this process repeats. So through this interaction with the environment, through this random mutations, you end up with creating an object, an animal or some kind of organism, which is actually able to survive well in its environment. And in that sense, this intelligence, it emerges as a consequence of some basic rules. So to an extent, you could say that the perspective of reductionism has shifted. We kind of have a reasonably good understanding of the process of how evolution works, but we don't, necessarily understand how the fully, emerged object, in this case a human, actually can be explained. It's a very complex, interaction between millions of years of these kinds of processes interacting with a very complex physical environment and other organisms as well, which eventually results in the construction of this object. So this is a kind of, a paradigm shift in some sense, as to trying to stop explaining the result, but explaining that rather the process by which the result emerges. And that's what I would mean by, in some sense, emergent AI. That's really the paradigm shift, which I think is behind the success of current AI technologies. So in this sense, it's very hard to fully explain the resultant complex behavior, but you can explain the process of construction. So just to hammer this point home, we could make an analogy here where we have, for example, in the human case and evolution, you could say, well, there's some kind of genetic rule which maybe we understand reasonably well, but this interacts with the environment, and another, to some genetic mutations will turn out to be beneficial, which will then get also mutated, again interact with the environment, and over many, many eons, this will actually result in the creation, the emergence of this intelligent behavior. And in some sense, you could argue that the meaning of this word intelligence is nothing more than a process by which simpler objects or organisms go through a process by which they become more able to survive in the environmental conditions which they live in. And that's the meaning of intelligence. It's just really, in some sense, this process. And analogously, in machine learning and AI, we have learning rules, which in principle we understand very well. We can write them down, and they interact with a complex data environment and maybe even a physical environment in things like robotics. And these data will then tell you, okay, your current predictions are working to a certain degree, but you can then adjust them again to improve, in the light of the data, or maybe even the changing data, the prediction. And this process iterates. We understand well the learning rule. The data may not be, in some sense, fully understandable, but this iterative process again results in the emergence of a powerful mechanism, namely a predictor, which can hopefully function well in the environment, the data environment in which it's been trained. So in this sense, it's there's a kind of analogy here, and it's very much the case that machine learning in this viewpoint is a data-driven approach to AI. So this is really, I should say, this is the perspective of machine learning. We are not necessarily going to be able to explicitly, or even we don't bake into the construction necessarily the idea that we can understand in a totally reductionist sense, the resulting algorithm or the resulting object, but we do understand the process by which it's constructed. So in that sense, yeah, machine learning is this mechanism, is this process in which we use data to drive the derivation of these algorithms. So it has no necessarily explicit explanation of the end result, but only explicit rules on how to learn the result. So this is very powerful, actually, and you can take it almost to extreme simplicity. You could say, well, look, imagine you want to play a game like Go here. So a very simple algorithm, which would be our reductionist rules, would say something like, well, when the board is in state X, then you try and move Y. If eventually, when you're in that state X and you made a move Y, you won that particular game, well, the next time you play the game, well, and you see the same state X, then you should make the same move Y. However, if you ended up losing the game, then you should try something else, right? This is a very simple algorithm or a simple rule. But if you do this and, against an opponent, your environment, and you try this many, many times, eventually this will converge to a very, very powerful player. So the clever part, though, is in some sense how to represent the board, right? So you won't be able to see every possible state of the board, X, because there's so many of them. So how do you do that? How do you generalize to situations which you've not seen before, right? That's really the key idea. So this is the underlying heart, if you like, of the algorithm, but we do need to be able to generalize away from states that we've not yet seen. So this is the idea of deep learning. It's a kind of machine learning, but with just a particular way to represent the state space and to make predictions. So in deep learning, we have this, inputs, which might be an image or the state of a board in a game like Go. And to some extent, this mimics the processing that might happen in organisms, natural organisms, in like brains, where you might then go through a series of layers, which then result in an output. And the idea is here that these layers are doing nonlinear processing, and they're looking for pattern matching in a recursive sense. So this unit here might fire, like in analogously to a neuron in a human brain, if there's a certain kind of set of pattern which is present in the input. And similarly, this neuron might fire if there's a different kind of pattern input. So if you go further down, this neuron might fire if there's a certain pattern in the preceding layer of neurons, and vice versa. Or continue, as you continue to go down through this network, you then get this recursive patterns within patterns within patterns sort of recognition approach. And then you can learn all of these parameters of the network which are determining which patterns should be recognized. And this gives an extremely powerful pattern recognition system, which is very, very useful. And it's very well tuned to the kinds of problems that we often encounter in AI, in the sense that when you're thinking about things like computer vision, you're often recognizing that a visual object actually might itself be composed in this hierarchical sense, where there might be certain kinds of, a tree itself is made up of trunks, which is made up of branches, which is made up of leaves. They also have this hierarchical structure themselves. So many of the objects in the real world, also language, has a hierarchical structure. There are paragraphs, sentences, words, characters, which also appeal to this decomposition recursively of patterns within patterns. So that may be one of the reasons that we see these kinds of structures in natural organisms and why they are also so successful in an AI context. So some of the challenges, though, around this, is that in general, you need a lot of training data to train these kinds of deep learning systems, or an awful lot of parameters. The predictions are typically quite hard to explain because that was not necessarily the way that we thought about this. As I said before, we explain how to construct the process by which these algorithms are made, but explain the result of them is hard. It's very hard. Also, the machines currently don't necessarily have a particularly good understanding still of human language, and also the physical world is, they don't have necessarily a really good understanding of the physics and how objects are interacting with each other. Another big issue is that people don't really trust machines, and they think maybe that's partly to do with the lack of an understanding into how they work, but also I think people don't really see these machines necessarily as helpful. They maybe see them as a kind of threat, maybe even to their working lives, or they don't see them necessarily in a beneficial sense. And I think there's some work to be done to try to address that. So I'm going to talk now a little bit about some of the specific work that we are engaged in at UCL. There's a whole vast array of stuff, but I'll just give you some brief overview as to some of the research. And also, as I mentioned before, much of it is with an interest in what we can do with it. We're not just theorists, we do care about the ultimate applications of these things. And so some of these have been successful in becoming spin-out companies, which I can also hopefully share with you. So some of the interesting things about vision research are, given this three-dimensional world that we live in, how can you model that? How can you make machines to better understand the structure of this three-dimensional world, and how do objects appear in it, particularly when you don't have a three-dimensional camera, you only have these two-dimensional projections. So understanding things like depth, perceiving where objects are in relation to the camera is very interesting. And maybe if you don't even have explicit labels about these objects in the world, how to use unlabeled data to understand how they relate to each other, these objects. So here's one particular project which is along those lines. And so hopefully you'll be able to see the video very soon. But in this particular project, the computer is going to make a three-dimensional model of a human face. And as it understands then the structure of the movement of the face, it can actually make a three-dimensional model from just the camera, this two-dimensional camera of the image of the video feed of the face. And then when it does that, it can reimagine or recreate a video of the facial movement and on another person, or the same person, but spoken in a different way. So for example, you could have somebody speaking in, say, English, and then you could understand the physical structure of the way that the mouth and the eyes and the nose and the cheeks all move together. And then you could have, say, somebody speaking in Chinese, and also understanding what the mouth and what should be the physical movements of the face in order to be consistent with Chinese. And you can interpose these on each other. So I'll try to hopefully show you this here, and you can even if you're interested, go to see a video demo on this thing by going to this link. But here's an example of this. I hope you'll be able to hear it. Don't think we've done the wide looking. Okay, let me just try that again. Okay, just give me 1 sec. Let me try to. Sorry, folks. For some reason, it's not playing. So maybe we can. Let me just try one last time. Okay, I think I'm afraid going to have to stick with just images. Okay. Yeah, I'm sorry, folks, but for some reason the videos are not playing. So okay, we'll have to just make do. Okay, so anyway, this lady, if you would have been able to hear it, she's actually going to speak in English. The computer will then model this lady's facial movements, and then they will actually have another actor who's speaking Chinese, and actually then make this lady appear as if she's speaking Chinese. So make a new video in which her mouth movements will actually be consistent with the Chinese language. So it's actually a very interesting and cool demo. Let me, again, I don't know if this is going to work, I'm afraid. For some reason, it's not going to allow me to present. Let me just see if I can. Oh, gosh. Okay, so this one also, I'm afraid, is not going to play, but this is another interesting example in which we can try to, from a single camera, we can actually estimate the depth. So how far away is an object from the camera? And doing this, we can then actually understand, for example, where to place a character in a virtual or in an augmented reality game like Pokemon Go. So the company that makes Pokemon Go is Niantic, and they bought this UCL company, and they're now able to then place the characters in this augmented reality environment, which is actually, for example, behind a tree or in front of a tree, because we understand how far away from the camera that tree is. So then with that understanding, we can actually place the characters in a meaningful position in the image. So this is a very, very nice problem. And again, another demo which you're not going to be able to see is another spin-out aerial AI, and they make a very interesting problem, solve a problem which you're trying to solve the pose estimation. So given all of the limbs in your body, can you understand where they're positioned in real time? So this company made an algorithm which can run on a mobile phone, which can then do this in real time. And there are a whole bunch of applications for this. And this was just bought by Snap earlier this year. Okay. So in terms of language research, we're also very interested in how to use language for solving real-world problems. And again, another video, which I'm afraid is not going to probably play, is that we'd like to be able to use natural language to understand very large amounts of textual communication. So if you think about something like, for example, a bank or an insurance company, they will actually have an awful lot of communication, both with customers and clients in a textual form through emails or customer feedback, but also internally within that organization. People are emailing each other all kinds of requests and all the time. So you spend probably something like 70% of your time as a worker in a bank or an insurance company just dealing with textual data, just processing these things. So the question is there a way to do that more efficiently? Could you make a machine which could, in some sense, read those texts, understand whether or not there are certain requests within those texts, and automate the response, or help the human to actually then, say, look up automatically in the database the information which is being requested in that document, and then send that automatically back to the requester. So that's something that this another company, Reinfer, is doing. It's actually then helping to automate these kinds of processes at scale. And there are huge applications for this. You can imagine also things like governments and here in the UK, Department for Work and Pensions, who are dealing with thousands and thousands of applications for various kinds of social benefits, for example, every day. How can you process these applications more efficiently? And also get a sense of really what your organization is doing. One of the big challenges around when you're thinking about the modern world is that actually it's very difficult for organizations to understand what individuals are actually doing. It's very hard for senior management to get a good understanding perspective of what your organization is actually doing on a daily basis. And by understanding automatically the content of emails and text documents, you can actually amalgamate this understanding to a macroscopic level, and then present the results to senior management, so you can understand as an organization where actually your bottleneck points are in terms of the information processing at scale. All right, so yeah, so another interesting, I think, challenge is how do you deal with the fact that you need a lot of training data for these deep learning systems? Also, there are other interesting aspects that even if you've got this amount of training data, you can rapidly go out of date. So if you think about, for example, COVID, we had a situation in the past where people would be applying for bank loans, maybe, and the algorithms were trained on data from, say, 2 to 3 years ago. But now the situation has changed. People's personal circumstances are no longer the same. The economy has moved on. The application loan to give a loan or not actually should should also reflect those changes. But the data has changed, and how do you then rapidly try to update your systems? Not necessarily with a huge amount of new labeled data. So you want to, as quickly as possible, use the new data that you have with as little human labeling effort to retrain these systems quickly. So this also brings us to the point that, well, actually, we also don't need necessarily people to label these or to be strong coders during this machine learning construction process, but we do need to get the experts' expertise. So what we really care about is not necessarily making breakthroughs in terms of the AI, but we need breakthroughs in terms of how to get the information that humans have into the AI systems. So that's a kind of very important part of this AI process as well, how to make humans actually interact with machines in a much more natural way, such that the machines themselves can understand much better how to solve these problems. So in this sense, also people in general have a much richer understanding of the problem than we may give them credit for. So historically, we might have been asking people to label things, this is a cat or not a cat, but people actually have a much better understanding of what a cat is or what a dog is. Maybe, and if there's some way to get that information incorporated into the machine more quickly, that would actually help hugely with the labeling effort. So here's one example of that, which is a very old idea, but let's imagine that your task is to learn an animal classifier, and I gave you some images here, which are all unlabeled. The machine doesn't know any of these kinds of animals. And what would be the standard maybe approach in machine learning? Well, you'd simply ask everybody or somebody to label all of these images. So that's toucans, a fox, etc. And once you've got all the labels, then you'd ask a machine learning algorithm to try to find a statistical relationship between the image and the corresponding labels using that process we talked about before, maybe with deep learning. But it's very time consuming to label all of these images up front. Maybe there's a better way to do this. One way to do this would be that you ask a human to label some of these points. So these images here might be labeled, for example, as a bear, and then the machine looks at some of the other images and says, okay, well, this one here, for example, if the human says, this one's a bear, then the machine might look at all the remaining images and say, well, this thing here looks kind of similar to this, so that's probably a bear. And similarly, this thing also looks a bit similar to this thing, so that's also probably a bear. So the machine thinks it kind of knows what's going on with this one and this one, but then it goes to some other image, say this one, and says, well, that doesn't look like anything I've seen before, so could the human please label this for me? And the human then labels this particular image, say a crocodile, and then the machine repeats, and it goes through to some other images. So this one here, that looks very similar to something I've seen before. That's probably a crocodile. Similarly, this one is probably a crocodile. It goes to some other image. This thing here, though, looks like nothing I've seen before. So human, please label that for me. And this process repeats, and very quickly, the machine will then start to get an understanding of all of these kinds of animals, without the human having to label explicitly all of them. So with a much smaller amount of human labeling efforts, the machine will start to build up this picture as to what an animal looks like from each different class, without requiring the human to exhaustively label all of these images. And this is the active learning labeling paradigm, which can be very useful also in the real world. So we've been looking at this, where on the x-axis is the amount of data that we've labeled, on the y-axis is the prediction, and a kind of natural language processing problem. And what this image is trying to say is that if you select these images using the blue curve in a sort of a smart way, you can actually rapidly increase the performance of the prediction compared to just selecting these images randomly to be labeled. So this actually can then result in a much more rapid training and much less data labeling effort than would ordinarily be required. So similarly, we have many interests in practical natural language processing problems Like, if you got a very large database, like Wikipedia in some sense, you might have a question like, what's the last time the LA Dodgers won the World Series? And this is typically a very consuming process in terms of time and memory. The machine then tries to answer this question. But actually, maybe you can do it more quickly. So we've been also developing approaches which are very accurate, but also much, much faster than traditional question answering systems, and many other related problems within natural language processing. All right, so I want to move on to another topic, which is action research, so how to interact with the environment. So as we mentioned before, there's a kind of interest in things like coming up with these simple rules, these underlying paradigms for how to explain, how to create a machine which can play very well. There's a slightly different idea which we came up with a few years ago, which is actually called expert iteration. And essentially, this is a kind of a very interesting paradigm in which you're trying to get a machine to play a game like Go or chess very, very well. And the idea is based upon the intuition that you might have, for example, if you think about a human expert, they may think, very deeply about a problem. They may look at the chessboard, and after some time, they will say, okay, this is the move I'm going to make. Right? They think use all of their experience and their in-depth, knowledge and processing very, very deeply. They think about it and say, okay, this is the particular move I think we should make from this position. And then what you could have is essentially an apprentice who just says, aha, given this particular board position, the expert took that particular move. So I will learn that. I will rapidly try to understand, with the kinds of positions that are presented to the expert, which of these positions are likely to be, or from these positions, which moves are likely to be good ones. And so the apprentice can take this, and they can then use this to rapidly suggest to the expert, okay, you should actually only consider, let's say, these 10 moves. These are probably the ones which are going to be good. And the expert takes each of these 10 possible moves and studies them very deeply and says, aha, of these 10 moves, that's a particular one I would take. And again, this builds up into the database of, given a board position, what would an expert do? And you can make this process then repeat. And in our particular case, the expert is a deep neural network, and the apprentice is also a deep neural network, and we can iterate this process through this expert iteration, and you actually end up with an extremely powerful game playing mechanism. So this algorithm is the same algorithm that AlphaGo and DeepMind used to make the leading game playing systems. It's exactly the same algorithm. We published basically just a little bit before them, but the key thing is you also need a lot of compute power to run this in the real world. So essentially this algorithm and a lot of money equals a very good game playing system like AlphaGo 0. So we didn't have that kind of cash to spend on training these systems, but essentially it's a very simple idea, but again it results in a very powerful learning mechanism. So the algorithm that we came up with, which was also used by DeepMind, basically when it's trained on a different set of games, essentially beats not just human performance, but all previous algorithms which have ever really been played or used to play these games. So it's a very, very powerful idea. Similarly, we're interested in multi-agent reinforcement learning. Unfortunately, again, I don't think the video will play, but you can understand then how to control various characters in games to result in very strong play and strategy. You can do more practical things. This is just a demo here, but there are various objects here, blue and red, and they are learning to collaborate, these objects, and they have a battle in this simulation. And the idea here is that the blue agents are cooperating together, and the red agents aren't, and the blue agents somehow beat the red agents collaboratively. And similar ideas can be used to then control things like car fleets. And so this versions of this algorithm have been used by Didi in China to control and manage their fleet of cars. And similar control theory problems can be addressed in this multi-agent reinforcement setting. So very briefly, I want to tell you about other work that we're interested in. We're interested in how to generate data, so how to make models which can generate, for example, images and text and maybe even video, how to do that in an efficient way. So this is some work actually done by NVIDIA, but there's some nice images here, and these images are faces, of course, but these are not real people. None of these people exist. These are just fake images, if you like, or generated images from a computer. And as you can see, the state of the art is pretty impressive, and we're very interested in this kind of approach. There are some, I think, very interesting advantages being able to do this. And one of them is that if you have a very good generative model of images, you can actually use it to compress the data very effectively. So we've been working also on compression algorithms which are lossless, so there's no loss of information at all. And then we can take an image such as this dog, and we can remove reduce the file size to roughly half the size, and not lose any information at all, so that we can then we can decompress the algorithm, sending only half of this bits, and then reconstruct this image perfectly. And how do we do this? Well, we make generative models of images, and if we understand the structure in some sense statistically of images, we can exploit that to make highly efficient compression algorithms. This is currently some of the world's leading compression performance. Here, there's still a lot of work to be done to make this maybe more practical and to speed it up, but there are also very interesting benefits and applications in areas like medical image compression, video streaming, things which are really, really bandwidth heavy. Similarly, we're very interested in challenges around drug and molecule design. How do you try to explore the space, the vast number of possibilities for how to design and develop new drugs? Maybe there are more efficient ways to do that based upon an understanding of molecular structure, but also using past databases of how molecules perform in certain kinds of environments and situations. We're also very interested in general in the problem of data efficient machine learning. You might have robots which are trying to learn how to manipulate their arms, but you would then want to generalize to situations they've not seen before with very limited training data. And we're also very interested in these physical systems where these robots are acting in a real world. There are physical constraints by which they're operating. And similarly, you might think about problems like weather prediction, which we're also working on. We know that these systems also obey certain kinds of physical laws and constraints. How to incorporate these constraints such that the predictions from these AI systems are actually physically meaningful. All right, so that's really pretty much all I wanted to say. Just give you a whistle-stop tour of some of the things that we're doing at UCL. There are many other things, of course, going on in terms of research, but these are some of the things I think that you might find interesting. So in summary, I think AI systems are pretty amazing. We've made tremendous progress, but we still maybe don't. We're not there in the sense that these systems still don't have a really great understanding of the physical world around them. And I think that's going to be very important for the next step. We certainly need to think of better ways to train these systems without so much explicit human labeling. And I mentioned some of the approaches that people are looking at there, including us. Active learning is one such idea. There are related ideas around unsupervised learning, weak labeling, etc. And I think we're beginning to see the benefits of AI interacting in the real world. We're getting these real, self-driving cars, which are, becoming a reality. This is very, very important and very interesting. And I think also the interaction with humans in the real world is also going to become, as a kind of a co-worker. You start to see these machines, hopefully in a positive sense, that they will be helping humans in their daily lives and also in their jobs. So overall, I think the future is very bright and very optimistic. Of course, there are some challenges here, but in general, I think machine learning has a huge, the positive potential impact on the way that we do things in the real world, and I would very much encourage people to bear that in mind when thinking about their research. So thank you very much. You're very welcome to email us here or myself at the AI Centre, and please, if you have any questions, I'm also very happy to answer any that you may have now. Thank you.
So thank you very much, David. In fact, there are a couple of two or three questions. If you could take them, if you have the time.
Sure.
Yeah. So one question is, there are a lot of comments on YouTube that we see. Largely, it's a very wonderful session, good session. So one person asks, with the advancement of AI and machine learning, what would be the role of human beings in future? Whether they will use them in their own advantage or fully dependent on them? Well,
it's hard to say, but to be honest, I try to not get too involved in highly speculative questions because they're always really hard to answer. They're very interesting. I think, to me, I view machine learning more as an incremental process, a bit like that evolutionary one. That amoeba, millions of years ago, wasn't thinking about the consequences of what might happen right down the line. It just makes some an evolutionary change which is useful for its current situation. And I think in a similar way, for us, it's really about trying to find things which people find useful. We are making, I think, algorithms and devices which are going to be of utility for us, right? I think that's the important thing to focus on. And yes, there are going to be maybe philosophical questions about what's this all leading to and what's the future of humanity, etc. But I think we also need to focus a little bit on actually making practical, usable things that people care about, and I think that's where I prefer to focus the conversation. In the here and now, what can we do this stuff? Yes, of course, we need to be cognizant of the potential downsides of these technologies, if there are any, and mitigate those issues. But try to sort of stay with the the realities of and solving some of the problems that we currently have. In medical, how to make better medical devices, how to remove some of the menial work that people are doing. Those are the kind of things I personally prefer to focus on.
Well, I have another question, David. It's about your question answering. So the person asks, why is the UCL approach 2,800 times faster? What was so specific in that, in the question answer?
You'll need to look at the research paper, I'm afraid. It's all very technical, but it's essentially a smarter way to do the processing using some pre-caching, as far as I remember.
Okay. And I have probably the last question, which is on, is deep learning a revival of artificial neural networks? And it says, do you think it meeting the same fate that happened to the traditional artificial neural networks a few years back?
Yeah, that's a very good question. I mean, deep learning is indeed there's no difference. They are artificial neural networks. It's maybe to some extent a rebranding of the phrase, but with the emphasis on the depth, I think that's really maybe why people came up with that phrase. That people were looking at artificial neural networks, of course, many years ago. There's nothing new in this idea, and it's gone through a variety of various in fashion and out of fashion stages. But I think what was, people were very keen to look at these multi-layer neural networks years ago, but the reality was it was very difficult computationally to make progress there. We just didn't have the compute power to really do it. So people tried, but it was not very successful. But I think the deep learning, of course, it is an artificial neural network. There's no no doubt about that. And many of the structures that you can see would be very familiar to people 20, 30 years ago. There's no surprise really there. But I think the emphasis is that what people have, I think, discovered is that if you are able to have these multiple layers, people are talking now about hundreds of layers, even greater in some of these systems, that actually the performance benefits we're seeing do come from the depth of the network. That's really a key insight, I think, which has emerged over the last, say, 10 to 20 years, which is, maybe why people are emphasizing that it's the depth of the system, which is really, really important.
Well, maybe just one more, a very short question is on the explainability in very deep learning models. So perhaps it's a long question, but the sense is that is it going to be a real problem? The deeper we go in terms of the neural network size, the more difficult it would be to explain. And then how do we justify, how do we justify the use, or how do we explain the use?
Yeah, I mean, I think this is a very interesting question as well, and it's difficult, and I think there's not any simple or easy answer to this, and I think it will depend very much on the application. So, you could ask a similar question to a human, right? You might say, okay, please, Mr. Surgeon, explain to me why you are deciding to do this operation in that particular way, right? And he or she may be able to come up with some explanation, but the reality is that it's a very complex thing, which is somehow based upon all of their personal experience, their education, etc. It's a very complicated thing to explain. Similarly, why did the human driver turn the wheel at that particular moment, and the car crashed and maybe had some unfortunate consequences. How do you explain that in a reductionist sense? Exactly why the human did exactly that thing at exactly that time. That would seem maybe an impossible question to answer, and maybe an unreasonable question even to pose to the human. So I think there are certain situations where these algorithms might be applied in which you may be okay with not having an in-depth explanation. So if it's a self-driving car, again, it may be very difficult in a reductionist sense to fully understand why the machine did that at that particular time. It's still, a complicated interaction between the training data and the machine trying to do its best. And you may be fine with that. You may say, look, that's okay. I don't need that. All I need is some confidence that the machine is acting accurately, in those situations. So it's more kind of, you might shift the burden to a performance requirement rather than an explanatory requirement. So similarly, we don't necessarily expect humans to be able to explain all the time why they drive the car like the way they do, but we do expect them to do it well. That's, in a similar way, you might say there are certain machine learning and AI applications where similarly the burden is not necessarily on explainability, but it's rather on the performance. And similarly, even in more classical engineering situations, I think you could make a case that people don't necessarily understand, fully, like, well, how does a space shuttle work, or something very complicated, but just that it works is the important thing. It's very hard to take this reductionist approach to the whole thing, but these complex mechanisms and objects necessarily have to perform at a high level. On the other hand, though, there are certain situations where you would like an explanation. You very much would like to be able to say, maybe explain why that bank loan was given or not, or why that particular judicial decision was supported by the algorithm in a certain way. So I think there are it depends on the application. There are some situations where I think even in the human case, we would expect the judge to be able to explain their decision, but we wouldn't necessarily expect the driver to be able to explain the decision they took at that instance as to why they would move the steering wheel in a certain direction. So I think in a similar way, but with different requirements for machines for the different problems that they're addressing.
Well, there are a couple of more questions, but I think due to paucity of time, I would request people to directly reach to David. He has already, it's very easy to find David. You just Google and you're on the right page. So there's no issue with that, and you have the contacts. So thank you very much, David.